Welcome to the presentation for the Portable Buck Converter Battery Electric Vehicle Charger, or BCEVC for short. This presentation was done by Amr Marey, myself, and Ahsan Elahi, my partner. So a little bit about the project. This project was done as a submission for the Portable Charging System for Electric Vehicle project. This project was designed by the MathWorks Excellence Innovation Program. This project specifically Project 216. It was an excellent project. We really enjoyed working on it, and they have a lot of interesting projects that we recommend that everyone checks out. The the files for the project and the documentation and everything is provided in the GitHub repository provided in the description. Please check it out. We would really appreciate it. If you have any further comments, you can comment on there, or you can comment on this video, and we will definitely look into it to see your question / comments. So before I begin what exactly that we're making, I should describe the problem statement. So the thing is, in recent days, the battery electric vehicles are becoming more and more popular around the world, as the world needs to shift to renewable energy sources. Climate change and other external factors are forcing us to transfer to renewable energy. However, for battery electric vehicles, one issue that they might face is that they can run out of charge before reaching the nearest charging station. This problem can also technically happen with internal combustion engine vehicles. You can just run out of gas and there's no charging station nearby. In that case, you would tow your vehicle, which is expensive and takes up time. However, for the portable, for an electric vehicle, what we propose is we propose a portable charging system that you can carry, let's say, in the trunk of the vehicle or maybe somewhere else. And this charging system will charge up the battery within the electric vehicle temporarily, let's say for only a few minutes, and then you can use that little charge that you have to reach the nearest charging station. So the charging is designed to be only used in emergency, and it's not really designed to replace actual charging stations that are in place. So the charging circuit is just simply a buck converter. So ideally, the reason we chose buck converter is that it's simple, reliable, and there's not much to it. It's portable, so you want to make the circuit very simple. So in this model, we have Vi as the voltage of the portable charging system, and it's the open circuit voltage, and S is, and then you have the buck charging circuit. Vo is the voltage of the battery within the electric vehicle. As I said, it uses a buck charging circuit, and the parameters are provided below. The open circuit voltage for the open circuit voltage for the charging system is just 500. L was chosen to be 750 microhenry. C was chosen to be 1 microfarad. The battery of the electric vehicle was modeled after the battery of the Tesla Model S, one of the earlier models, I believe. As such, the nominal voltage of the battery can be shown to be 346 volts, and the current capacity is 345 ampere hour. How these numbers came to be and why we chose these specific circuit parameters, like for the electricity and capacitance, you can read more about that in the documentation in GitHub. There is a lot of good sources, and we recommend that you check it out. Anyway, the control system, and then after that, so after we design the charging circuit, we design a control system as such that the battery electric vehicle is charged safely, and it needs to be safe, it needs to be reliable. So for the sake of simplicity, we decided to go with simple PID control. The reason is that PID is simple, it's reliable. However, for future models that we might design, we might abandon this and go for a more advanced form of control. Uh, so the idea is that going back to the system is that the the current actually being monitored is the inductor current and not the current flowing through the voltage. However, if you actually do the circuit analysis, you see that the average current flowing through the inductor is the same as the average current flowing through the battery. And this is why a buck converter was chosen, is that it provides a continuous current at the output, which simplifies control for us. The reference current was set to 50 amperes. So this number was chosen as such that it's reasonable and doesn't set a high stress value, a high voltage stress on the switch present within the buck converter and so on. The PID parameters found through the frequency tuner provided by one of the MATLAB toolboxes are shown here. KP was 7 out of 1000, KI was just 10.5, and KD was 0. These were the optimal parameters. And the measurement delay block, the Z inverse that you see here, simply exists only within this model to avoid an algebraic loop. You can read more about algebraic loops in the GitHub repository mentioned in the description. The reference a link that directs you to a MathWorks webpage. Next up, we have discussed thermal modeling as well. We have the main thing with regards to thermal modeling, of course, are the semiconductor materials, so the diode and the MOSFET. Both components were modeled, but the thing is, we assumed that there was no direct interaction between the diode and the MOSFET, because the relation is negligible. The diode does not dissipate heat as much as the MOSFET. The MOSFETs generally the switches in any charging circuit is usually the main source of loss. So the switch is the main relevance here. And if we were to really focus on the diode, we would be wasting simulation time for no real reason. The heat dissipation of the MOSFET averages to be 300 watts, and combined with 2000 centimeters squared of copper, we get that theta GA of around 20 Kelvin per watt, assuming that convective heat transfer is still in the air. After thermal modeling, we have discussed the battery management system, or the BMS. So what the BMS is that it is a system that estimates the state of charge present within the battery of the electric vehicle. So we decided to stick with the Coulomb counting technique. That's how the BMS is modeled. So all it is just this. It claimed that the state of charge is just simply the 1 over C, where C stands for the for the current capacity of the battery, which was 345 ampere hour, multiplied by the integration of current that has been flowing through the battery. So this is a good technique, but it's very simple. There's a lot of problems with this technique. For example, it does not consider temperature effects. It doesn't consider you need to know the initial current flowing. You need to know the initial charge that was present, and so on. As such, this technique is very, very simple and has a lot of problems. However, we decided to stick with it for the sake of modeling only, as the main focus is to model the charging circuit and not the BMS. If we were to go with a more advanced battery management system, simulation time would be very, very slow. So we had to make some compromises just for the sake of modeling. And now we will show our models that we have designed for the BCEVC. This is the first model that we have of the BCEVC. We have 3 models in total. Now, the first model is designed just to focus on the electronic side of things. It doesn't consider the thermal modeling or the battery management system. The reason was this done is to provide a very fast simulation speed and just really investigate the electronics and nothing else. That way we have very good details on what's happening from the electronic side. Anyhow, So as mentioned, the device is controlled through PID control, as you can see right here. The reference current is set to 50 amperes, and IL is fed from the output to here, and here is the general PID control. Now this is the buck converter circuitry. The parameters are set to for the capacitance, they're set to 1 microfarad, and here they're set to 750 microfarads microhenry, sorry, and so on. The voltage of the external battery that's charging the EV is set to 500 volts, and the EV battery, which is modeled after the Tesla Model S EV battery, has a nominal voltage of 246 and a rated capacity of 345.53. The initial state of charge was chosen to be 10% for this, as in general, it is probably a valid assumption that you will have a low state of charge if you're trying to charge the EV vehicle, because this charging system was designed to be used in case of emergencies where you already have a low state of charge. So as such, I set the state of charge to be 10%, which is a reasonable assumption, I believe. Anyhow, we can see through this multiplexer, we can find the state of charge of once the thing is charging. We can simulate the control system and see the increased state of charge. We can see the current flowing through the EV battery and its voltage. Now, let's run the simulation and see what happens. Now here's the simulation is running, and now it's finished. As you can see, the state of charge increases perfectly as expected, and increases at a very reasonable rate. The current, it starts off at 0 and has a little overshoot to approximately a bit less than 200 amperes, and the steady state current in general is approximately 50 as expected, with a current ripple of no more than, the current ripple, as you can see, is just 1 ampere, which means that there's a 2% error, and the voltage is approximately constant as expected. In general, the results seem to be very good, and as such, the model gives promising results. Okay, next up is Model 2. Model 2 is much more detailed. It considers the thermal modeling and includes a basic battery management system. And however, its disadvantages is that it has slow speed, and we consider the EV battery to just be one large cell, just to avoid slow simulation speed. Anyhow, let's get into the detail. So, as you can see, we have the usual PID control here. Nothing different than what we had before, except we had to make a little adjustment for the sake of SimScape, because here we're using SimScape Electrical. As such, we had to model a driver circuitry, which is just a PWM generator and a gate driver, nothing really too complicated. And here you can see the circuitry is the same as what was in the first model. However, the thermal modeling is included for the MOSFET and the diode. So for the MOSFET, this is the thermal modeling. We have an ideal ambient temperature is taken to be 300 Kelvin, which is about 27 Celsius, and you have an ideal temperature source. A convection heatsink was an area of 2000 centimeters squared, and heat coefficient of 20 watt per meter squared times Kelvin, and yeah, it uses passive thermal modeling. And same thing for the diode, nothing really different. And yes, so as you can see, it is very similar to what was there. And the battery, I forgot to mention that the battery also has similar parameters, the exact same parameters to what was in the first model. Now, here is the battery management system in order to approximate the state of charge. So, in this we chose a very basic battery management system. The reason for this is to provide fast simulation speed. So we used the Coulomb counting technique, which is just described by this equation. However, there's several problems with this equation. One, it neglects the temperature effects, and two, you need to know the initial state of charge, which is not known beforehand, and which is usually not known beforehand in real life. Three, the error from measuring current can accumulate, and once error accumulates to a very high error, you will not get an accurate reading. However, we chose it for this model just for the sake of fast simulation, but in reality, we would definitely consider it to be to have a different technique. So for the sake of this model, we consider the initial state charge to be 10% like the first model, and that's it. And that's it for the battery management system. So anyway, we run and we see everything. So once you run the model, this is what you'll see. So here's the EV battery information. It is similar to what you see in the first. So the state of charge is increasing, as you can see from the last figure, which is what we expect. The battery current stabilizes at 50 amperes, which is what we wanted, and the error is much like before, and the error from this model, it shows that it is only 0.1 ampere, so negligible. Errors can come from, unfortunately, errors can come from using different models in Simscape and Simscape specialized power system, as each have their own equations and how they're programmed in the first place. So in reality, we'd have to do an experiment and really see what the current exactly really is. Anyhow, what the current error exactly really is. And the battery voltage stays constant as expected. And the battery charge, it increases over time as the state of charge would definitely, as the state of charge increases. So next up, we need to investigate the diode and the MOSFET heat flow, and mainly what's interesting mostly is the net heat flow, which is the summation of both. So this is the result that you get from the net heat flow. It decreases a little bit, then increases eventually, but it's still within reasonable range. And that is all to provide, I believe. Here's Model 3. Model 3 is identical to Model 2. The only difference is that in Model 2, the EV battery was treated to be one giant cell, and the voltage of that cell was just modeled after the voltage and the rated capacity of the Tesla Model S Tesla Model S EV battery. However, in this case, we actually try to model the architecture, the cell architecture of the Tesla Model S layout. The Tesla Model S cell battery structure consists of 16 modules in series, whereas each module is identical to all the other modules. And inside each module, sorry, it's just taking a bit slow. Inside each module is 74 sub-modules in parallel, And as you can see here, so if you count the number of modules in parallel, you have 74. And inside each sub-module, you have 6 battery cells in series, and these are the battery cells. These are the properties of the battery. Each battery cell consists of a nominal voltage of 3.6 and the battery charge, and here is the cell capacity. The exact specific cell is actually provided in the GitHub repository, so I recommend you check that out if you want more details. But yeah, other than that, there is really no difference from Model 2 and Model 3. But the issue is, in Model 3, we're technically modeling 7,104 separate cell batteries. This makes the simulation speed very, very, very slow. Frankly speaking, I could not run it on my computer. As such, I cannot search through the simulation right now. However, if you have a really powerful supercomputer, I recommend that you can try out the simulation and see for yourself if the result would work or not. And I would love if you could report it to me. But I expect that it will definitely work, and it's just all I did was just try to have a more realistic model. That's all. But it still should work. And with that, we conclude the 3 models, and that's it. We will go back to the presentation
now. As shown from the 3 models, the BCEVC showed promising electrical characteristics and lied within safe heat ranges. As such, in the future, we may attempt to advance these models and eventually build a prototype of the BCEVC. If you have any questions or suggestions, please feel free to comment below or put your questions or suggestion in the discussion section of the GitHub repository. Again, the GitHub repository is provided in the description below. A bit about us. So we are 2 undergraduate engineering students from the University of Alberta. We are both passionate about renewable energy, and we hope that our project can add to the discussion as the world shifts to renewable energy sources. I myself, I'm Amr Marey. I'm a 5th year electrical engineering student, and my partner Ahsan Elahi who's also a 5th year chemical engineering student. We will both be graduating in May 2023. Before we conclude this project, I would like to thank MathWorks for creating the MathWorks Excellence in Innovation program. This project was done for Project 216, Portable Charging System for Electric Vehicles. The program really highlights new innovative problems that students can work on, and it's very interesting to see new problems and try to read about the problems and maybe find ways that you can find new solutions to these problems and read about existing work. We would also like to thank MathWorks senior research scientist Roberto G. Valenti. He reviewed our project and really gave insightful comments on how we can improve our models and etc. It was an honor to participate in the program, and we encourage other people to enter the program as well. Thank you.